systems engineering. So let me try to tell you a better fairy tale about systems engineering. So let's say that we're going on a journey together. You know, we start down here where it says start, and we go to where it says finish. And so, you know, along the way, we have some bridges. Now, these bridges represent significant items such as risks. Because no journey is, you know, completely easy. Otherwise, you know, it would be trivial. And as we know from fairy tales, bridges are guarded by trolls. And this isn't just any troll, it's a statistical troll. And so, you know, you see the bribe schedule there. And so you can bribe the troll with, you know, 10 gold pieces or 30 or 60, and you have, you know, various different chances of getting it. And you notice that trolls don't spell very well, of course. Now, if you have a big bulging bag of gold pieces, you can just pay this troll and not worry about it. You know, one in, you know, to the 12th is not a bad, you know, set of odds, even if you have to experience it a bunch of times. Now, some of these bridges don't have trolls, they have bridge guards, and they're toll bridges. The guard won't eat you, but they absolutely will not let you pass unless you pay, you know, a substantial fee. Now, this might be a technology development that you can just, you know, spend all the money on and retire the risk completely. So there are some things where you can just completely retire the risk, or to the level where it's completely inconsequential. And so here we see all of the trolls and the bridge guards. And furthermore, we can say that perhaps these bridges have different costs, which are represented by piles of gold pieces. And so if you pay nothing, then your risks are up in the red, right? And the more you pay it down. And so if you paid all 5, you'd be down in the very bottom of the green, right? And you notice that the toll bridges are kind of expensive here too. So the more you pay, the lower the risk goes. So we never have enough gold pieces to pay for everything we'd like to pay, unfortunately. Now we could choose a path through here like this. And so we pay some, we get this guy pretty nicely down in the green. We pay this toll bridge, we pay this toll bridge, and we arrive here and we're almost out of money. And so we pay just like half a gold piece, and these guys whack us pretty hard in a risk sense. And so this is clearly not efficient, right? Because the risk is entirely dominated by these you know, last guys right here. And so a different path, you know, you might choose a different path like so. Now, you know, you still want to kind of avoid this guy because he's expensive and scary looking. And so you really don't want to take this loop at all. But maybe, you know, and you have to pay some of these guys. You have to pay this one, you have to pay this one. But maybe you only pay this toll bridge. And then, you know, these guys are kind of cheaper. And so you'll notice that whatever the amount is that I paid all of these guys, they're all in the low yellow, which is not as good as being in the green, but at least they're all even. And so, you know, this balance, this is a better overall risk posture. And this is what we call risk balancing, because it makes absolutely no sense to kill one risk and have the other risk be a tall tent pole. And so basically you try to keep them all approximately even. Let's see. So that's all nice. But let's say, how do you know where all the risks are? So let's say you come to this fork in the road, right? You can see a cute little troll here, but he's still a troll, and, you know, why take any risk at all, even with a small troll? So, you know, you look at this and you think, why don't I go to the left around this mountain? But of course, the problem is on the other side of the mountain, there's this big hairy troll. And, you know, in retrospect, you should have gone the other way, but at this point, it's too late, you know. So again, how can you tell where all the risks are? Well, you can hire a wizard to do analysis. And, you know, and they can foresee all the risks. But the problem is wizards cost gold pieces too. They're not going to do analysis for free. So what about that? Well, maybe, you know, tribal elders have been known to give away advice for free. And sometimes they won't stop giving away advice, even when you wish they would shut up, right? But nonetheless, you know, you can sift all of the advice that you get from the tribal elders for the advice that's useful, the experience that's useful to you. And so, you know, by using tribal elders and wizards, you can figure out how to, well, by doing all of this, you can figure out how to allocate your limited gold pieces to trolls, bridge guards, wizards, and toll bridges, and have a as low a risk as possible space mission or whatever else it is that you're doing. So I hope that kind of sticks the idea of risk balancing into your heads in a new way. Now, there's many stories that could be told about Stardust, and I'm really just going to tell you one of them from kind of my point of view. See if you can spot the dead skunk when it shows up. Okay, so Stardust was the 4th Discovery mission. It was selected in November 95. And it was the first larger mission that kind of followed a standard selection process. There were some that were retroed into the Discovery program. The Discovery program continues to be a competitively selected, medium-sized science mission. Actually, they're the smallest sort of deep space science mission, right? Planetary science. These days, a Discovery mission still costs $500 million. It was less back in Stardust today, but it's really hard to run much of a mission for less than that. At least that's the current thinking. So it was enabled by recognizing that aerogel, which is it's sort of a ceramic thing that it's a ceramic material that's mostly empty space. And because the material has a low enough density, it can sample hypervelocity particles without just vaporizing them. And so recognizing this, the idea was, well, why can't we go to a comet and sample the comet particles by collecting them in the aerogel and still having something worth analyzing when we're done. So the main requirements on the mission were to collect the sample and survive, because of course you're deliberately going into a hypervelocity particle stream that are coming at you at, as I recall, 10 kilometers a second. And so you can't hit very many of those and survive, obviously, without them hitting the protection that you have with you, which I'll discuss in a minute. So the first requirement is to collect samples and survive. And then the second requirement is to return the samples to Earth. And that's pretty much it. I mean, there were cameras, but the real point was go get the sample and bring it back. The cameras were kind of just for context. So this was the fastest Earth return that has ever been done. It was almost 2 kilometers a second faster than the Apollo returns, because of course it's coming in hyperbolically rather than just from the moon. The required entry flight path angle error was 0.8 degrees, which you can think of as being 5 kilometers wide. If you think about it in the B-plane, it's basically you have to hit 5 kilometers. And so if you target this from 6 days out, which is a nice early time to do a maneuver, to be kind of relaxed about it, relatively speaking, you have to control that last maneuver to 5 millimeters per second to get 5 kilometers. So plus minus 5 kilometers. Assuming there's no other errors, of course. And the target size is both because of the survival of the entry capsule, but it's also for human safety issues, right? Because we're returning this to the Utah Test and Training Range. Salt Lake City is not all that far away. And so if you miss by very much, you tend to drop stuff on Salt Lake City suburbs, which is, not a good thing. So anyway. So here's the spacecraft configuration. So, for requirement number 1, survive, it has these Whipple shields, and you see that they're composed of several layers of, thin metal. And so the idea is that a particle hits the first metal, vaporizes, and spreads out enough that when it hits the second level, it stops. And even if you get several in the same spot, you can take several holes, and still survive. And so the solar arrays are protected, and the main spacecraft body is protected. And this is the, launch vehicle adapter ring, which can be trashed once you're off the launch vehicle because you're never going back. There is, you notice it has large solar arrays because the trajectory took it out to 3 AU. It's not a very big spacecraft. As spacecraft go, 385 kilograms is, smallish. And you see the sample return canister here. It's in the sampling configuration. This is the aerogel collector. And then later it gets folded up in here and the back shell closes. And then it gets released and dropped into the atmosphere. And there's a parachute, up in here. Now, the propulsion system, in this view, it's kind of there's 4 clusters of thrusters that are all down here on the corners of the spacecraft. And their thrust vectors, I've kind of drawn coming out of the top of the spacecraft here, these 4 thrust vectors right here. All the thrust vectors point more or less on the plus Z axis with just a little bit of offset to provide additional roll about Z. So I'm going to be talking, so these thrusters are configured in an unbalanced configuration. And by unbalanced, I mean, so when you're trying to maintain attitude control, you fire various combinations of thrusters. And so for any pair of thrusters that you fire, you get control about one axis, but you also get a delta V on the spacecraft. And so because they generate torque and delta V inescapably together, they're called unbalanced thrusters. If they produce torque but no delta V, then they would be called balanced thrusters, or correctly nominally balanced thrusters, because nothing's ever perfectly balanced, but it's a whole lot better than this, which doesn't even try. Oops, let me go back one. Okay. So Stardust was, like I say, in the 90s, developed in the midst of the faster, better, cheaper mania, right? And so back then it was important to say faster, better, cheaper as fast as you could all together, because that just made it all better, And the problem with the idea is that we can do things faster, better, and cheaper. The reality is that you only get to pick 2 out of those 3 at most. And, unless you have some really new way of doing things. If you have a new way of doing things, great. You can do things faster, better, and or cheaper. If you just say, we shall do it faster, better, cheaper, well, that works about as well as outlawing the tide coming in, it's like, forget it. So the Discovery program was supposedly willing to accept more risk. And so that is one dimension that you can adjust, but it turned out that the risks were higher than they actually wanted. And so it didn't really end up that way very well. So Stardust was one of 3 NASA interplanetary science missions that were launched within 3 months. So this will test your historical knowledge, perhaps. Mars Climate Orbiter was launched in 98. As you see, MPL was launched in January of 99, and Stardust was launched the next one up. And 2 of these came to a very bad end. It's kind of interesting that Stardust was one of these 3, which in many ways, because they were all built by the same manufacturer, had significant similarities in terms of the avionics, which I'm not really going to get into.
Were they all launched from Cape Canaveral?
Yeah, they're all consecutive Delta launches, Delta 2.
Why select the winter months? Why select the winter months?
It was just orbital mechanics. So anyway, faster, better, cheaper reminds me of a story that I heard growing up. And I will try to turn on a bit of an accent here, although perhaps you won't be able to tell the difference. So there's this farmer that was trying to teach his mule to eat sawdust. And every day he'd mix a little bit more sawdust into this mule's feed. And don't you know, about the time the blame thing learned to eat pure sawdust, it died on him. So that's sort of like faster, better, cheaper, right? You can make it as cheap as you want. Eventually it dies on you. Stardust did outlast the other 2 spacecraft by 11 plus years, but, to some degree that was luck. Part of why MCO and MPAO failed was the faster, better, cheaper thing. And like I say, Stardust came really close to failing. I don't want to say too much bad about the early Discovery program. I think overall it's been a success. And maybe it couldn't have happened without a certain amount of faster, better, cheaper, but it certainly went too far, at the beginning. So I want to say a little bit more about Mars Climate Orbiter. I guarantee you that you've heard about Mars Climate Orbiter, even though you don't think you have if you can't remember the name. So this is Mars Climate Orbiter. And you see the thruster locations there, and you see the big solar array hanging off to the side. And you immediately think, my, what a lot of solar torque this spacecraft experiences, right? And because all the thrusters it turns out that this also has unbalanced thrusters. And so whenever you deal with the solar torque, you're going to produce delta V on the spacecraft, right? And so mismodeling of the reaction wheel desaturation delta V led to the burnup of the spacecraft in the Mars atmosphere, in September of '99. Now, of course, the problem was that the plane of sky error, and this was mostly an error, you know what I mean by plane of sight, there's like line of sight, and then there's plane of sky. And so the cross line of sight thing that's hard to see with typical tracking data, Doppler, for instance, was not very observable. And, everybody knows, right, that this was a units problem. Has anybody not heard the thing about the units problem where, we lost the spacecraft, right? So everybody knows that, and everybody's wrong, because the units problem was the straw that broke the camel's back. While it is large, it is still a very light plastic drinking straw, right? And the thing that actually broke the camel's back was big bags of fragrant bad management, right? And so that's what did most of the damage. And, the management failures included hindrances that were put in the communication between nav and attitude control people, insufficient resources. We also foolishly retired the only good deep space plane of sky data type. So we couldn't see what was going on because we thought we could model this, right? And, while the MCO failure would not have happened without these bad management problems, I still assert that that this shows what unbalanced thrusters can do to you. They can kill your spacecraft. Now, back to Stardust. So thrusters are the only attitude control actuator. The attitude is maintained by deadbanding all the time. Now, just in case some of you don't know about what deadbanding is, let's assume I'm a spacecraft, right? And I'm slowly drifting, this way, and I want to straighten up. So I fire thrusters on this side. And then when I get back to the other side, I fire thrusters on this side. And in this case, all of these thrusters point up. And so I'm gradually pushed up, even as I'm, maintaining my attitude like this in 3 dimensions, not just one, right? So there's no reaction wheels. There's no control moment gyros. There's no magnetic torquers. There's no little pixies, moving the ends of the solar rays. It's all thruster deadbanding. And like I said, the thrust is all in more or less the plus C direction, spacecraft plus C. Now, the pulse frequency depends on, the deadband size in each axis, right? If you have tight deadbands, you tend to bounce back and forth really fast. If you have loose deadbands, it's kind of more sedate. It also depends on the solar torque, right? If the solar torque is banging you pretty hard against one axis, it doesn't matter what the deadbands are. You just have to keep firing to maintain attitude control. And, the solar torque on Stardust was relatively large because of the large solar arrays. So the magnitude of the deadbanding could be as large as 55 millimeters per second per day. If you did this for a week, if you did this every day for a week, you'd be 100 kilometers away from a ballistic trajectory. And so that means you have to predict, remember, we're trying to hit a 5-kilometer target. So that says right there, you have to do 5% of just the deadbanding to be able to hit a 5-kilometer target, a week later. And maybe you can't actually do that. So, one good thing is that each thruster pulse was reported in telemetry. It recorded the time of the firing, which thrusters were used, an onboard estimate of the delta V, which isn't always super useful, but so, and the reason is that when you have these monoprop hydrazine thrusters, a cold thruster produces half the impulse of a hot thruster for the same pulse length. And so the onboard algorithm doesn't know about that. On the other hand, with this information, you can reconstruct all of that on the ground in principle. It is good to have a separate telemetry stream that only tells you when a thruster fires. If you try to pull it out of channelized telemetry, the problem is that you tend to run out of channel. You tend to run out of bandwidth. And so a lot of the rest of the attitude control data was limited to being very infrequent, like once per hour. Whereas at least we got every single thruster pulse firing in a little, 50 byte packet or something. So, attitude changes are performed by thruster slews because, again, that's all there is. So if you want to change the spacecraft attitude, you have to slew on thrusters. There's a whole lot of reasons you might need to slew. You know, if you're doing imaging, if you're doing telecom, if you need to thermally decontaminate the instrument, the camera. If it goes into safe mode, it says, I have to point at the sun. And if it can't, if in some cases, it will not only point at this, it will point a little bit off the sun and kind of rotate about it, which takes an awful lot of delta V to maintain because it's an unprincipled axis rotation. And then, of course, there's trajectory correction maneuvers, which we'll discuss more in a minute. So all of these slews are implemented, you know, in a, you know, Euler slew about a particular, you know, whatever axis is convenient. And they're, you know, have a trapezoidal profile, right? The rate, you accelerate up to a certain rate, you hold that rate, and then you just decelerate down. And so this is the target, and the controller controls, you know, to more or less that. And so, you know, if you look at this, you know, most of the thrusting is going to be at the beginning and the end, but there's going to be some in between because you seldom are doing a principled axis slew. And so there's some Euler, you know, stuff you have to do in the middle. Now, the slew delta V's could easily be 200 millimeters per second because of the low spacecraft mass and because the thrusters had very little cancellation. So predicting the slews to a few millimeters per second is correspondingly difficult. Here's some actual data from a particular slew. This is millimeters per second of acceleration over 7 minutes. And you can see that it kind of follows that same profile. There's a burst of thrusting at the beginning, and then it kind of goes to a low level, you know, for the main part of the constant rate slew, and then it fires a lot at the end. But the thing is, it's, you know, this is not a nice, clean thing to predict, is the point I want to make with this, right? So all spacecraft attitude activities generate delta V. And just, you know, there's a lot of things on the spacecraft that are attitude activities that have an attitude component. And all of this stuff in the future, you have to predict, right? If you want to hit a target that's in the future, you have to know every single attitude thing that's going to happen accurately enough to not mess up your targeting. You know, you miss the target, or worst case, missing the target is pretty fatal if it's the return capsule, but you can also miss the target of a flyby so badly that you cannot recover and get it back to where it needs to go because there's not a ton of propellant on board. So here's sort of an example of a prediction of what we're going to have, you know, in sort of notional time future, right? We start out with standard deadbanding, and then we might go to tight deadbanding for comm because, you know, you want to point the antenna more accurately to get higher bit rates. And then we go back to standard deadbanding, and here we do a slew, you know, a big slew to put sun on the camera to kind of try to bake off whatever was accumulating on it because that was a thing. And then, you know, we come back and we do another comm session and so forth and so on. And this is all very fine until safe mode hits right in the middle. And so when safe mode hits, remember, it suddenly says, I have to go point at the sun. And so it does, you know, a lot of delta V. And you know, then it goes back to standard deadbanding, and it does not do all of this other stuff down here. And so, as you can see, a significant position error accrues from the unplanned delta V if you integrate the difference in these two curves, you know, and that error in position has got to be corrected by a later TCM to get back on course. Now, have you figured out that the unbalanced thrusters are the dead skunk on this spacecraft? So let's talk about TCMs for a minute. If we want to do this is a trajectory correction maneuver. So you're firing the thrusters deliberately to change the velocity now so that you change the position later, right? So the TCM thrusters also only point in one direction. And so if you want delta V in that direction, you have to slew somewhere and then fire the thrusters and then slew back, okay? Now there are some spacecraft that can do vector mode maneuvers where they have thrusters pointing every which way, and they can just fire a little bit of that and a little bit of that and get where they need to go. Mars exploration rovers, Curiosity, Perseverance spacecraft of that type, and others. But turn and burn is also a common implementation. So the sequence of activities for a Stardust TCM is you slew to an attitude, you inertially hold once you get there, you do the main burn, and then you have to rate damp, and you inertially hold for a while after that to make sure that the timing all works out, and then you slew back and go back into normal deadbanding mode. Now, all of these generate delta V. And it turns out most of the delta V is generated by these slews. And so, you know, you can think you want to go to this attitude, but when you add in all the slew delta V, the total delta V goes somewhere else. And so then you have to change the attitude that you go to, and you have to iterate on that until it converges to close enough. Like I said, the slew delta V prediction errors were the largest, were the dominant term, especially for smaller TCMs, because they're the largest delta V besides the main burn. Now at JPL, we have a statistical TCM error description from 1963, which is a while ago. And it talks about proportional errors that scale with the magnitude of the delta V, and fixed errors that you always have no matter how big the delta V is. And you can see that you RSS them together, and if you plot them, you're going to plot something like this, right? And you can see that for small delta V, the fixed errors dominate, and for large delta V, the proportional errors dominate, right? So for Stardust, the fixed errors are mostly due to the slews that get you to and from the burn attitude. Usually, we care about the fixed errors for the final targeting maneuver because the final targeting maneuver wants to be small. And so a small burn really cares about the fixed errors. Now, the requirement on the fixed uncertainty was 6 millimeters per second, 3 sigma in each axis. Now, we started seeing errors. Again, this is generally slew prediction errors of order 100 millimeters per second. And when you see 100 millimeters per second, you don't know if it's actually the worst that you're ever going to see. And actually, let me go back. The 6 millimeters per second is represented by this cute little troll. Okay. So we adopted a fixed uncertainty of 150 millimeters per second, which is 25 times worse. And if you blow this little troll up by 25, he's not so little and cute anymore, is he? Right? So this was really annoying. We had pointed discussion with the spacecraft developers, and they ridiculously tried to say, oh, the main burn meets the requirements, but that's ridiculous because the main burn is not the entire activity. And we've already seen how the main burn had to be adjusted on account of the, slew delta Vs. So, because again, it's the accuracy of the total activity that matters for targeting. And this is where I started saying Stardust is evil. Now, by evil, I don't mean in league with the devil, okay? But it was really, really annoying. Now, it's also a challenge, and you'll see how we met it. But in my mind, I still think of Stardust as being evil. So what does this mean for the Earth return? Remember that the first requirement was survive, which at this point in the mission had already happened. The next thing is to return the samples, because if you survive and don't return the samples, it's kind of useless. The pictures are not worth the mission. EDL, of course, is entry, descent, and landing. It's a JPLism. It's, coming home, right? So we started to ask, what about EDL? What does this mean for Earth return? So we usually move the final TCM close enough to the end so that we can tolerate a fixed error. And if we were going to do that here, because, the fixed errors, as you move them in, their effect gets smaller and smaller. The proportional errors are more or less constant throughout, because if you get closer, the maneuver gets bigger, the proportional errors go with it. So they're more or less, flat. But for fixed errors, you just move the maneuver as late as you have to. Problem is, it'd have to go to 4.75 hours out. And that's assuming there's no other errors. So actually, you would need to go a little bit later than that. And that's a big problem because the release is at 4 hours. And not only that, but you have to, before you can do the release, you have to verify that the targeting is correct due to human safety concerns. You can't just assume everything's working and push the button. National defense will not let you do that. And so basically, our entry, descent, and landing plan does not work. We are in flight and we have a broken plan that does not work for the spacecraft. So what do? Well, we come up with a new plan, of course, but assuming we can. So let me talk about the updated EDL plan that we came up with. First of all, the Genesis return happened 16 months before Stardust. And while that return didn't go well for other reasons, the planning, the thought processes from Genesis were a big help in understanding what the real human safety requirements were, public safety. And of course, you know, if sloughs are a problem, then we just don't do them, right? So, and so that means that you have to do biased maneuvers. If you're not going to do sloughs, then you have to bias the targeting such that you can keep all the required delta V in one direction or close to one direction. Let's suppose that we have to make a control of plus and minus these red arrows here with respect to this 0 here, right? If we have to do exactly this, then obviously we have to be able to turn the spacecraft 180 degrees. But if we had previously introduced a bias such that we were always going to do this bias delta V, even if we were perfectly targeted, then we could keep the direction, you know, the same and just do more or less. Now it costs us the bias delta V because we're going to pay more or less that regardless. But now we have eliminated the turns from this maneuver. So that's a way to kill sloughs. And the final maneuver for Stardust was 29 hours out. It controlled nothing but the flight path angle. It was an in-place maneuver. It had a bias of 1 meter per second. And it basically moved the impact point from skipping out of the Earth's atmosphere all the way down to the Utah Test and Training Range. Now, you can also do this in 2D, right? If you need control in a 2D circle or equivalently a 3D sphere, right? You can also introduce a bias delta V like so. And instead of having to do, you know, a 2 pi or 4 pi, you know, sort of set of maneuver directions, you can now limit the maneuver directions to within 30 degrees, as I'm kind of showing here in cartoon form. And so the larger the bias, the tighter the spread, right? Although the larger bias has its own costs. So the next to last maneuver at 10 days out was to control everything but the flight path angle. And so particularly to control cross track. And so it was biased so that we could use small sloughs that were much smaller, implemented as deadband walks to get to the burn attitude. And so this bias magnitude was 1.4 millimeters per second. Genesis also used bias maneuvers, but for different reasons. Now, biases this late are unusual, and they're actively avoided at JPL because it means you have to do the maneuver. There's no choice but to do the maneuver, or the mission will fail to achieve the objectives. We're used to canceling the last 2 or 3 maneuvers. You know, we'd like to do it that way. The last, for Curiosity, Mars Science Lab in 2012, the last maneuver was 8 days out, and it was 11 millimeters a second. And so the biases alone here are 1,000 millimeters per second or more. And so we're talking about enormous maneuvers compared to what we might do on a nice, clean spacecraft like MSL. So we had to learn how to do these bias maneuvers because this was not part of the pre-launch plan. We had to calibrate the in-place main burn because there were still some non-burn components. And so we had to short the main burn by the amount of extra stuff that was going to happen. We had to calibrate these deadband walks. You know, they still needed to be predictable, reasonably predictable. And, you know, we had to understand the rest of the system. There's also quite a bit of deadbanding over that last 10 days, which you know, has a component. So for the final maneuver, the deadbanding prediction was almost 50% of the allowable error, even cutting the development cycle as short as we could. We also had to, and the only way we could figure out this stuff was to run calibration campaigns on the spacecraft. And you'll notice here that we were running campaigns, you know, about 6 months before entry, which is not when you want to be doing this. You want to be doing this pre-launch, or at least when you have enough time to do it again. But this was the only time we were going to be at the right part of the solar range. And so we had no choice, and we had one chance to get it right, pretty much. There was an earlier campaign in 2003, but at that point we hadn't figured out enough what we needed to do. So figuring out stuff just before it's needed is not ideal for something, in a space sense. Now, there was still the safe mode potential, right? If the spacecraft has the wrong sort of failure, it's still going to go and point to the sun. It's going to do that with lots of delta V, and that can destroy the nice targeting that you just set up. You may have to perform a TCM to cancel that, which introduces large errors, with big slews. And so there are windows of vulnerability where it's not at all obvious that safe mode will immediately save the spacecraft, but it will destroy the mission, which is kind of bad. There were backup maneuver opportunities, but they would not have guaranteed success for every contingency. So the plan is still scary, right? The last two maneuvers have to happen or there's no EDL. We have to set up these biases for the last two maneuvers correctly, or there's no EDL. There is a backup opportunity at EDL 3 or 4 years from now, 3.5 to 4 years, but we, are not even sure that this is going to, the spacecraft's going to last that long. So as I said, at Mars, we're used to canceling on mass maneuvers, not depending absolutely on having to do them properly. So what does this remind me of? Well, I had a former colleague, late colleague, who used to fly F-4s in Vietnam. And when he was talking about a nice way to do a landing, he said, yes, whenever I landed one of these beasts, I tried to get, 10 miles out, and I would line up on the runway, and I would line up on the glide slope, and I would just make tiny little corrections and just fly down the glide slope and right down the center line. And because it's an F4, you don't even have to flare. You just slam it into the runway and everything's fine, right? No last minute anythings, okay? Now, let's compare that instead to landing at the old Kai Tak Airport in Hong Kong, which I'm sure none of y'all, well, most of y'all have probably never done that. But I did, so I'll tell you about it. Anyway, so the way you land at the old airport in Kai Tak is you fly straight at Checkerboard Hill. You aim right at this. You just fly straight at it. And then when you get there, you turn right and land immediately. So I flew in there as a passenger, 45 years ago, and I remember looking right out the window, and there was Checkerboard Hill, not real far away, right? You can also see what's on TV in the apartments right around, very close to the flight path. Really, really close to the flight path. Now, in aviation circles, this used to be known as the Kai Tak turn. And in passenger circles, it used to be known as the Kai Tak heart attack. This is not a Photoshopped picture. And that's why Hong Kong has a new airport as of 25 years ago. They went and reclaimed a bunch of land out in the ocean, and actually they had very few accidents at Kai Tak for all of these shenanigans going on. But that's what Stardust entry, descent, and landing reminded me of. It's like landing at Kai Tak. You could do it, but why would you ever plan on that given a choice? You could also say, just because it worked doesn't make it a good idea. And even better, you could say, if it's stupid and it works, it's still stupid and you're lucky, which, I got from 70 Maxims of Maximally Effective Mercenaries, which is just a great comic strip. I mean, online comic strip that y'all should all go read sometime when you don't have anything better to do. Now I'd like to finish the talk with a few good things about Stardust, because there were some good things about it. So we got the samples back, and the scientists said all sorts of wonderful things about the scientists, and I'm sure that science is still going on, with that. I'd like to show this video. This is a video of the entry, which happened at night, and so that's the capsule, the white thing in the middle, glowing in the infrared from a NASA plane, DC-8, and so you can see that it's getting brighter and brighter, and it's starting to have a halo around it as it's heating up the atmosphere. You can see the wingtip coming into the view right there. And as it continues, it'll even start to leave a trail behind it. You see how it's leaving a trail of ionized gas or whatever behind it. So it's really amazing that we were able to, capture this. This was in 2006. So, I'm sure we could do a better job now, but it really is pretty remarkable to be able to see that. let's see. Yeah, I want to go on to the next page. Okay, yes. So, you know, here's the sample return capsule on the desert floor in Utah, and you can't tell it from this, but it was in the middle of a snowstorm, but we still, you know, it landed safely and we went and found it. Um, the samples are curated at Johnson Space Center, same facility as the moon rocks. You can actually go see the sample return canister. It's in the National Air and Space Museum, and I've seen it a couple times there just for fun. It is the most traveled human object on Earth, human-built object on Earth. I don't know, maybe ISS has traveled farther, but hey, it's not on the Earth, is it? So anyway, and you know, we did get an extended mission out of it. We went back to Temple 1, which was the deep impact target. And we were able to see where the crater is. If you kind of squint, it's not a very good camera, but we were able to see that there was kind of a broad, shallow crater where the deep impact impactor, you know, hit the comet. But, you know, the best thing about Stardust is that it's dead and gone and not bothering us anymore. Here you see navigators celebrating that they no longer have to navigate this evil spacecraft anymore. So anyway. Maybe that's not the only reason they're celebrating, but I like to think that it's at least part of it. So let me review in closing the lessons that we learned from Stardust. The first is that unbalanced thrusters make everything complicated. They tie everything together, which violates the keep it simple, stupid principle. If you keep things separate, it's much easier to do the systems engineering on small chunks of stuff than big chunks altogether, right? Second, don't assume that you can predict the behavior of unbalanced thrusters. Every time we have flown any thrusters, we have always found that their behavior in flight did not match what we expected. It's hard to test thrusters on the ground. There's always weird stuff that happens in flight. So do you really want to risk that they will behave in a way that, you know, are unexpected? Now, both of these items relate to having many important details. So I have a warning about that. And the warning is that orbit determination is full of a million details, all of which are trying to kill you, as you see in this picture. Now, this is, you know, true of space in general. It's true of aviation, submarines, nuclear power. Anything that you can't get out of or turn off quickly has this detail problem. And, you know, we try to mitigate these details as much as possible, and we pay careful attention to those that are left. But you can only pay, but it's very hard to always pay enough attention to the details. And remember that one of them will eventually slip through. And so the less details that can kill you, the better, because one of these days, you know, you'll have a bad day when it slips through all of the protections. So anyway, returning to our list, big risks in mission ops can sometimes be fixed with modest hardware changes. You know, for Stardust, if we had had small reaction wheels or balanced thrusters, we could have made Stardust EDL much less risky. You know, they would have been more expensive, but on the other hand, we spent quite a bit of money figuring out how to do it post facto, and there was still some risk that we were unable to retire. And finally, be careful about flinging dead skunks. You know, don't be turning your problem into somebody else's problem. Try to wear the big hat and do the right thing, okay? And remember, of course, that near-term solutions can sometimes cause serious long-term problems. You know, same as in life, right? Short-term reward, long-term reward sort of thing. Now, Stardust became evil because the systems engineering failed to balance development and mission ops risks. Now, maybe it was hopeless to expect better for Stardust, starting from faster, better, cheaper. But I think we can do better now. I think that good systems engineering across the whole project in both development and ops can be something that isn't just a fairy tale. So thank you. I'll take any questions now.
Thank you, Tim. Any questions from live audience here? Go ahead. Great talk. So I just want to know more about, I think there is only one mission that JPL lost where spacecraft completely missed the Mars and there was not even a Mars capture. And I think it was one of the three missions that.
Yeah, it was MCO.
Okay. So can you talk a little bit about what went wrong?
Well, yeah, so the orientation of the spacecraft was such. So this is Mars. The question is about Mars Climate Orbiter. So Mars Climate Orbiter is the only spacecraft that we lost at Mars, that we've lost anywhere because of a navigation error. There was Ranger 3 where we did a maneuver and suddenly the miss was twice what it was supposed to be because the maneuver had been done in the wrong direction. But Ranger 3 was not going to hit the moon anyway. And so that was at that point essentially an engineering test. So I'm going to kind of not count that. But yeah, we lost MCO because it hit the Mars atmosphere. The problem is that the spacecraft orientation was such that the delta V due to the thrusters was pushing it down toward Mars, okay? And so the units problem meant that instead of pushing it down, of unit 1, it was pushing it down of unit 4.4. And so the prediction going forward was that it was going to be pushing down at 1. And as we got closer and closer, the solutions were coming lower and lower, but we had no idea that it was as low as it actually was. Now, if you think about it, if we'd been going to the other pole, which we easily could have been, it would have been pushing it farther and farther away from Mars, right? And that would have caused other problems, but not, a burn up in the atmosphere, which is an immediate dead loss. So anyway, that's the proximal details. And then there was all the reasons behind it why we didn't know any better. So hopefully that answers the question. Any other in the room? Sure.
With the rapid expansion and emergence of kind of private industry, small scale distributed systems, do you see a trend emerging of faster, better, cheaper again?
Yeah, that's a good question. I mean, I've thought about that, not exactly in those terms. I mean, I think that, you can imagine sort of two ends of the spectrum, right? One end of the spectrum is we analyze everything in advance exhaustively. And then every time we launch something, it works perfectly because if it doesn't, it's a huge disaster. And it also costs a huge bag of gold pieces, right? And the other end is, it'll probably work. Let's test it. Let's launch it and see what happens. Yeah, interesting. Let's launch another one and see what happens. Interesting. Let's launch another one. You learn faster that way and it's cheaper. And so that's not exactly answering your question, but I think you can say the same thing for spacecraft, right? I mean, CubeSats have like a 50% on-orbit failure rate. That's not very good. But on the other hand, the investment in a CubeSat is small enough that you can afford to do that several times until you figure it out. And there's another, well, the talk tomorrow, in fact, I'm going to say good data beats good models, right? If you try something, you have data. If you think about something, you have a model, right? And so you'd much rather have several tests than a whole lot of thought. And another issue is thought is very expensive, right? Because you have to have wizards do it and they're not cheap, right? I mean, us collectively. And so, whereas if you just test the thing, right, then you can pay machinists to make another one, So I think that in some sense, you can think of rapid access to space and rapid development as a new thing that you could apply to allow some faster, better, cheaper stuff to happen in a good way. Because again, bad, faster, better, cheaper says your budget that you thought you had, cut it in half and do the same things, right? That never ends well, right? But this says we have a completely new thing that we're going to try, and it, has eventually, maybe not the first time or two, it's still worse, but then it over time, anyway.
Right, they picked two and they picked faster and cheaper.
Right. But, I mean, if it's cheap enough and it's fast enough, then eventually it gets better if you're willing to keep trying, right? And so that's sort of the risk the risk acceptance was supposed to be part of the deal, right? I mean, if you lose one mission in 10, but they all cost half as much, you come out ahead, right? But the problem is the timescales make that really painful. You know, if it's like a 10-year mission and then you discover that you've lost it. So it's much easier to imagine losing a mission that only lasted a few months and you can fly it again in a few months, right? So.
Yeah, just to follow up on that, I think I was reading that the tagline, failure is not an option. It was never said by anyone from NASA. It's just a movie line. And then on the other side, we have SpaceX, which is believing that if you are not feeling that
You're not trying hard enough.
Yeah.
Yeah, right. Yeah, failure is not an option. It's like, okay, what does that even mean? You know? I mean, there is a point where there are things that are worth working nights and weekends for. And you certainly shouldn't let something fail by not working nights and weekends when it's important, as long as you didn't plan in the nights and weekends in your budgeting, you know, so that you're forced to do that. It should, you know, if you take out all the slack in advance, then you don't have any slack for the inevitable problems. And so I would argue that the nights and weekends are to fix the inevitable problems, and that you should have generously margined things in the first place.
Any other questions, comments? Yes, go ahead.
Was there any sort of like decent rationale or decent argument for having the unbalanced thrusters? Because after your talk, it seems obvious that that's a terrible idea, but
Well,
these aren't idiots,
they're
right?
cheap. They're cheap. They're very cheap.
But is it really that much cheaper to put them all on one side than put them?
Well, I think, okay, to be fair, if you put them on the other side, there is the potential that they will somewhat contaminate the samples, right? On the other hand, you wouldn't have to use the ones that were balanceable during the sample collection, right? You could collect the samples in unbalanced mode and then use balanced thrusters when you needed the precise targeting. And so I think it was really just because it was cheap and we need to be cheap, and we can't be, you know, letting those whining navigators have us put thrusters all over our nice cheap spacecraft, you know. But I mean, I think to some degree too, it was well, so back then, I think it was not as obvious that this was a problem. Perhaps. Now, there is a spacecraft that we are relatively close to launching, and it has unbalanced thrusters. And I consider that to be a personal failure of mine, that I did not jump and scream and yell loud enough to get that fixed when I had a chance. I talked myself into thinking that it didn't matter as much as it does, and I was wrong. And so, you know, from here forward, I'm going to hopefully never make that mistake again. But I don't have a lot of time left to make mistakes. So, you know, anyway.